Day 3, give it up for day 3. I moved the room that I was working in because the building that I had been working in, its rooms kept getting reserved, so I had to keep switching rooms, and this is much more available and convenient for me. It is very underground. I would also like to apologize in advance for the noise of the fan. I can't stop it because I don't control the air conditioning and because I like to burp. But hey, let's stop complaining about silly things like staying alive and do some math, yeah? So today was actually really cool for me because we started learning about vectors in calculus. Of course, I see vectors in statics, and I see that we are going to be taught vectors in calculus 3, and I say, well, this is actually kind of cool. This will line up really nicely. But actually, vectors in math and vectors in physics are kind of different in a very interesting way. I talked about yesterday how vectors in statics are defined by a couple different things. First is the point of application, the second is the sense, the third is the line of direction, the fourth is the magnitude. But in calculus, vectors are defined by a set of coordinates. An x-coordinate, a y-coordinate, and a z-coordinate. They also share several different additive, scaling, and distributive properties. So despite these vectors being defined differently than in statics, we can still apply the same laws that we use. For example, the triangle and parallelogram law still apply. If you want to add a vector mathematically, all you need to do is sum its component parts. Here we see that the vector x, y, z plus the vector a, b, c will equal the vector x plus a, y plus b, z plus c. And you can do this for as many vectors as you want. Far more than 2, 3, 4, a billion, a Google. You can add as many vectors as you want as long as you know their component parts. And the cool thing about this is you get the same coordinates for the vector that you would using the triangle law or parallelogram law, and you don't need to draw a thing. You can also find the magnitude of any vector just by plugging it into the 3D distance formula. Pretty simple. And to be completely honest, I had some extra time today, so I have already gone and completed the section of math homework that this stuff corresponds to, and I feel pretty confident on it, so I think we're safe to move on to the next subject. So in statics today, we did a lot more practice problems than we did covering new concepts, but the new concept that we did cover today is really crucially important. So, since statics deals with situations and objects that have constant velocity, it means that the net force in the x direction and the y direction being applied in an object is 0. So as long as the forces in the x direction and the y direction cancel each other out, the object in question is in equilibrium. Now again, this does not mean that the object needs to be standing still. It can still have velocity. It's force and acceleration we're concerned about. Because if it has any acceleration, there's a force being applied, ergo, it is not in static equilibrium. Now, this actually gives us a really cool way to find unknown angles and magnitudes of the force vectors that are put in front of us. Because if we add all the force vectors that are affecting an object in static equilibrium, using the tip-to-tail method, it will make a closed loop. And because there's a closed loop, there is no net force acting on the object. So by using the tip-to-tail method, we can show that this particular system of force vectors is not at static equilibrium because it doesn't form a closed loop. But this particular one does. It does form a closed loop. And we can do some really useful stuff with this particular diagram. And here's how. The angle that is between two vectors on a free body diagram and the angle in between those vectors on this diagram are the same. So what that means is as soon as we make this loop diagram, we can use our sine and cosine laws to discover unknown values. Now, I know that this particular example is childishly simple and that things will get more complicated. I just don't have a more complicated example on me right now, and I'm sorry about that. But I'm pretty sure that when I do the homework in a few minutes, I will see more complex examples, and I will give you updates as soon as I finish. Alright, I won't be ashamed to admit it. It's been a few hours. But honestly, I'm really glad that I'm doing this now. It is really, really good to know exactly how long these problems and assignments take to do, especially this early in the semester. It'll give me a good benchmark to plan my schedule and my work around. So there are around 13 problems in the assignment, which doesn't sound that bad, but they are pretty hefty to say the least. I did almost 4 of them tonight, so that's almost a third of the assignment, which I think is a pretty good pace, especially considering that this assignment is due next Wednesday. So what I think I'm going to do is the problem that I got stuck on, I think I'm going to go into office hours or SI or see the TA to do something. But I think that'll be pretty good for statics for the night. So I am going to go take a dinner break, and then I'll be back to do some physics. Be right back. Alright, we're back. So the physics homework still isn't posted, which is a little bit disappointing because, again, I have time right now. I could really get some good work done on it. But it does leave me with one less thing to do tonight, which is a little bit convenient. But that doesn't mean I still can't go over the things that I learned in class today, and I should, because I really sort of struggled in class, but now that I have a greater grasp on the concepts, it would be good for me to review them. I opened the camera again and realized that I drew it a little bit high up, but that should be alright. Okay, so let's recall that the equation for Coulomb's law is as such, and it gives the force applied on a pair of particles given their charge and distance. As charge increases, the force increases. As distance increases, the force decreases. Let us also recall that the direction that the force is applied in depends on the charge of the particles. If you have like particles, the force is going to be repelling outward. If you have opposite particles, the force is going to be attracting inwards. So we know that there's a relationship between the charge of particles, the distance they are apart, and the force that they exert on each other. But there's a way to generalize this relationship so we can quantify how much influence a single charged particle has over its surroundings. These are electric fields. They describe how much influence a charged particle has over a certain point out there. As you can see, the mathematical definition looks a lot like Coulomb's law, except one thing is missing. The charge of the second particle is missing because the charge of the second particle doesn't matter. The magnetic field of a certain particle is determined by and exclusive to that one particle. Positively charged particles exhibit electric fields with vectors pointing outwards. Negatively charged particles exhibit electric fields with vectors pointing inwards. If you multiply the electric field vector at a certain point times a charged particle at that specific point, you will find the force that those two particles are exerting on each other. And finally tonight for physics, we have electric field lines. Now these puppies allow us to graphically represent the magnetic field of an object. If you draw a point anywhere on these magnetic field lines, the line tangent to that point on the magnetic field line will be the magnetic field vector at that specific point. The denser the magnetic field lines are, the stronger the magnetic field will be. For example, at this point right here, the magnetic field would be far denser than, say, the point right here. It's 9 o'clock and I didn't even need to do any physics homework. I wonder what my weekends are going to be like. Weekends, more like days I get to work fully on homework and studying. But I'm just complaining. It's 9 o'clock, I've been working since around 5:30, and that's really, really good. I'm very, very proud of myself for the work that I've put in today. So I think my blatant pessimism and bad attitude will probably be cured by a good night's sleep. So with that, I think I'm gonna call it tonight. Thank you so much for watching. I will see you tomorrow.